Hi folks, welcome to another allesfitter tutorial, and today we're going to tackle transit timing variations, or TTVs. Now here we have an example dataset that I simulated, so this is about the same as you would expect from one sector of test data. So we have about 27, 28 days, and it looks like there's two planets, one with a bit deeper eclipse, and then another one with a bit shallower eclipse coming here. So if we have a multiplanetary system like this, and I already give it away, so this is in a 2 to 3 resonance here, then we often expect some transit timing variations to happen because those two planets gravitationally interact with another. And through that cause slightly eccentric orbits and cause their transit timings to change over time. Now in this tutorial we're going to tackle how exactly are we going to fit for TTVs with allesfitter. The very first step for that is to do a normal linear ephemeridis fit. So here you set everything up exactly as you used to from the other tutorials. So I'm going to take it as granted, more or less, that you have done the other tutorials and you roughly know how to fit for two planets in a photometric time series with allesfitter. You can do this as explained in the other tutorials via the graphical user interface or directly in Python, whatever you like best. And I already did this step before, so let's just quickly check out what I had run here for this very first step, where we just fit a normal linear ephemeridis model, so we don't have any TTVs in this model. The usual settings: we fit for two planets, give the name of the telescope, we use a fast fit window, which will be important for the TTVs, shift the epoch in the middle, and I use the standard nested sampling, and we can go further on, but these are all the usual details. Plus I set the grid size to very sparse for the objects, just so it runs a bit faster. What kind of parameters do we fit for? Well, again, the usual stuff. So we have the radius ratio, r sum a, cosi, epoch and period for both planets. Fit for quadratic limb darkening freely in the Kipping parameterization, and we fit for the error bars in the baseline pretty freely. So here it's a very simple no red noise model. Now let's check what we found. If we look at the planets, then we see, oh, there's something happening. This doesn't look like a good fit, and that's not because the fit is bad, but it is because there's actual transit timing variation. So you see transit number 1 is like spot on here, transit number 2 is a little bit shifted to the left, so it arrives a little bit earlier than predicted. Transit number 3 is right on there, transit number 4 arrives a bit late, 5 arrives a bit late, and so on. This is for planet B. Now we look at planet C, and we see there's also some transit timing variations happening, but they're not as strong. So here we see a little bit late, a little bit early, a little bit early, and a little bit late. And number 1 and number 5 here are spot on. Inspecting those plots, especially the fit per transit plots, is a really, really important tool to check for these kind of transit timing variations, but also if you know there's some mean motion resonance going on and so on, so you would actually expect some TTVs to happen, then we can go through this procedure. Now, so this is the premise. You have your data, you already did a linear ephemeridis fit following tutorials 1, 2, 3 and so on. So now comes the new step. How do we do TTVs? Basically I set up the exactly same directory here with our data file, stellar parameters to pop up here, and we have our parameters file and our settings file. But now the important new thing is there's a few new functions that you can use. So for the linear ephemeridis fit, we did the show initial guess and the ns fit and the ns output. For the TTV fit now, there's another function that's called prepare TTV fit. So if we run this, it will print out what we see here on the screen. Namely, it's a couple of new rows that we can input into our parameters file. And it will create us a nice little plot. So let's quickly execute this line. As you see, this creates us a results folder, and it creates us two plots in here, which is preparation for TTV fit for companion B and the preparation for TTV fit for companion C. And as you see, as I flick between through them, we see it numbering and color coding the two companions. So companion B is the one with the shorter period. We see it has a total of 8 transits. Companion C has a total of 6 transits. And this is exactly what these rows here print us. Each transit has a TTV parameter that we freely fit for. So each transit can be offset a little bit. And if we look at the parameters file that we set up, we basically copy exactly the same parameters file from before. So you take the one from the linear ephemeridis fit, but what's new is you add those rows. You can just simply copy paste them from your console or Spider or whatever interface you use for Python, and you just copy paste them into your params.csv file. And these are all new parameters that we're going to fit for. So you see the number of parameters increases massively. Now the most important thing is that you will want to freeze the epoch and period parameters for all the planets where you want to freely fit the TTVs. This is because you need to have some linear ephemeridis, and that's why we're doing the linear ephemeridis fit in the first place. So if you look at the parameters file, then those 4 will now be frozen while before they were free. We can still freely fit the rest. But if we also set these to 1, meaning if we also fit those rather than freeze them, then there will be a huge degeneracy between those 4 parameters and all the TTV parameters. So we do want to freeze them to avoid this degeneracy. That obviously means that our linear ephemeridis fit will be slightly biased depending on, where in the sine wave we're sampling. So there are other clever ways. You could, for example, all tie them together by saying, oh, it should follow some kind of sine wave or whatever. But here we're going to approach it completely freely, just not putting in any model information. But we just see what the data will give us. And that's it for the parameters file. So not much of a change. In the settings file, the only change that we have is going to be this little TTVs thing here. The row fit underscore TTVs, we're going to set true. It was false before. And that's it. We leave all the other settings like we did in the linear ephemeridis file. We have our prepare TTV fit done. So now we can look at the initial guess, which will look exactly the same as the initial guess before. And then we can run our MCMC or nested sampling fit. In this case, we're going to run a nested sampling fit. And I'm going to start this now. And once it's converged, I'm going to zoom back in. All right, and we are done. And we find that our nested sampling fit has converged. We found about 50,000 samples. And in total for this big data set, this costed us about 15 minutes or 0.26 hours. So I said this is a relatively realistic data set, resembling test data. So that's quite a good speed for converging. It might be a bit slow on your laptop, but if you just want to play with this example, you could just truncate the data set a little bit to get it to run faster. Now, how does the result look like? We see the fits per transit. We see how it like wobbles around this green line, which shows the mean ephemeridis center. Arriving a bit late, arriving on time, arriving a bit early, arriving a bit late. And that's exactly what we wanted to see. So we actually see the TTVs in here. And if we look at planet B, then we also see he is on spot. He is a bit early, relatively on spot, a bit late, a bit early, very early, and a little bit early. So you see the TTVs are readily captured by the fit. If we check this in our corner plot, then we see there's actually really nice convergence here. So here we have our physical parameters, limb darkening, noise models, and then all these here are the TTV parameters. And we see they have a really nice convergence, and all of them are offset from 0. So there's not just sampling from the prior. By the way, the prior would be uniform, but this is actually like a nice convergence. We can check the trace plots for this as well. And here we see for the TTV parameters, this is the entire uniform prior we start off with. We see a clear trend away from 0 in some cases. So this is when the planet arrives a little bit early, planet arrives a little bit late, and so on. So that's great. Exactly what we wanted to see. And the final neat little feature are those little TTV underscore results underscore BOC plots that we see, where we just put the O minus C plot, so the observed minus the computed or calculated linear ephemeridis, or here it's titled TTV in units of minutes versus the transit number where it occurs. And we see there's a really nice like sinusoidal trend going on here. You can check this for planet C as well, and we see the same. So there's clear offsets, and that's by design of this simulated data set. We really wanted to have something that's very clear and stands out in the noise limits so we can see it by eye. But that's it. Thank you very much for watching this TTV tutorial, and I hope it will come in handy for you soon. Bye bye, see you next time.